We're actually quite a small venture. There's 2 owners of a company, and we've been working on this development, which we'll discuss towards the end of the presentation, for the last 5 months. So we're a very young company, so very different from the kind of mature players you've seen so far in this conference. Right. So what I'm discussing is the data pump. So the bit that goes between the RIP and the physical printhead itself. That actually conveys all of that information from the RIP software off to the printhead. So let's just discuss the data requirements that this thing needs to fulfill. Okay, so first of all, what I'd like to do is just clarify the basics of some computer units, because they're not as transparent as you might hope, especially not nowadays when they've changed the naming slightly. So we're all probably fairly familiar with SI units. Yeah, so everything's a power of 10 to the 3. Yes, so when I'm referring to bits, we're referring to a single 1 or 0 representation of data. And then if I'm referring to many bits, then in the SI notation, that will be a kilobit, as you expect with a kilogram, etc. A megabit, a gigabit, and so forth, all fairly logical and obvious. And then when we're referring to a byte, that's actually a collection of 8 bits of data. Okay? And so 1 kilobyte is 8 times 10 to the 3 bits. And then we have, obviously, the same convention, SI units, megabytes and gigabytes. And this convention is used for networking. So if you want to talk about how much bandwidth a network has, you generally talk in terms of gigabits per second, for example. Whereas if you are referring to things like data storage, because of the construction of the memory itself, we actually start to discuss things in terms of kibibytes, mebibytes, and gigabytes, which is really difficult to say. And these are all powers of 2, so you'll notice the exponent increments by 10 each time. So we go from a kibibyte, which is 1024 bytes, which we've already discussed, onto a mebibyte, which is 1024 kibibytes, and a gigabyte, which is 1024 mebibytes, yeah, and so on and so forth. And so it's pretty important to clarify at this point, because there's about a 7% difference between a gigabyte and a gigabyte, yeah? And so you have to be a bit careful when you're buying products, you don't get the wrong one. Someone might cheat you out of 7%. Or conversely, if you're trying to achieve a certain job, and you know that you absolutely need a certain bandwidth, you better make sure you don't get these confused, because otherwise you might be less 7% headroom. Okay, so most of you, I'm sure, are fully aware of this, but basics of dots per inch. Each dot conveys some level of information. And in a one-dimensional dot density, we refer to dots per inch. We're not really concerned too much about one-dimensional printing generally, I'd say. So we tend to have dots per square inch generally, which we're interested in. And nominally, if we have the same dots per inch in, say, the XY axes, then the dots per square inch will be the dots per inch squared. Why this matters is because the square law at play, so each square inch will actually have 360,000 dots. Okay, and that becomes important when we actually have to talk about data throughput. So you know, you double the DPI, you quadruple the data throughput requirements. We'll talk about that a little later. So how much data are we actually talking about here? So in this example, we're referring to a 40 kilohertz printhead. Okay, and we're saying that this 40 kilohertz printhead can have 8 discrete levels, so a grayscale printhead, 8 discrete levels. So from information theory, we know that we need 3 bits of data to represent this. So if we then find out that for 2,500 nozzles, 3 bits of data for each one of those nozzles, it's running at 40 kilohertz, then we need 300 megabits per second of data per head for a 40 kilohertz head. Okay? Now, we don't generally only require 1 head, so for a 4-color bar and 10 heads, for example, we're roughly a meter. If we ignore the overlap, then we're looking at 12 gigabits per second of bandwidth. So things are starting to stack up. We're starting to talk about an awful lot of data. Now, if we want to talk about buffering this data, for example, for 1 second in random access memory. So does everyone know what random access memory is? Yeah. Then we'll convert to gigabytes here because it's relevant. Okay. It turns out you're going to need 1.4 effectively gigabytes of store for that 1 second of print data. Okay. So let's do a little check here. If we had a printer running at 1 meter per second with 4 colors, we're effectively looking at 836 megabytes per second. And for 2 meters per second, 4 colors, we're talking about 1.67 gigabytes per second. So it's a substantial amount of data, huge amount of data, in fact. Okay, well, how does this match up with other devices which you commonly see in and around the place? So if we just have a look at this, then your hard disk drive, for example, conceptually you could want to store data on that. It's only running at 50 to 120 megabytes of data per second transfer speed. Yeah, the SSDs 200 to 500 megabytes per second. Of course, you can multiply these things up, have more of them in your system. Then other bottlenecks start to develop. The actual memory on your computer is generally at least 10 gigabytes per second, even for relatively modern embedded devices which will have DDR3 access. But it gets very complicated at that point because there's an awful lot of factors at work, and we'll discuss those a bit in a moment. So I suppose another question is, do we actually need a lot of these bandwidth, this bandwidth? And it all comes down to bandwidth and information transfer rate are equivalent. And so if you've got an image which is effectively the same information and you're repeating it over and over and over again, then obviously you don't need much storage for that. And so you are not going to suffer huge amounts of impact on the local store, and you can just repeat the image over and over. So it's all critically, it's about what information is original. You know, if you can store information locally, it's a really good idea. But what is the worst case? You know, what are we really designed for? We're designed for limits, and so we're dealing with things like continuously variable print. Then every part of your system is going to have to be able to cope with the bandwidth requirements which your printhead is going to need to satisfy. So, you know, we have to design for the worst case generally. So when we're talking about things like hard drives and RAM, we're generally talking about things which are quite local to the printhead. Of course, we have to concern ourselves with traversing the divide, say, between a computer, say, for example, and something which is actually going to be driving the signals into the printhead itself. So there's lots of industry standard data transfer mechanisms. Some classic ones like fiber channel. Everyone, I'm sure, has got a couple of USB devices. I think we got provided with one for this conference, in fact. And I'm sure people are familiar with such things as Ethernet, and Ethernet scales up to quite substantial bandwidths. So, for example, it's now not uncommon to see 100 gigabits per second Ethernet. And remember, we're talking about gigabits per second, not gigabits. Okay. So we have to be a little careful here because, especially in our industry, you can have a number of proprietary ways of transferring information across the divide as well. The problem with this being that you may well lose out on some of the functionality if you're not careful, because there's an awful lot of layers to a properly formed network transport protocol. And at the physical layer, you're dealing with transfer of raw data bits, and then you add on extra layers of complexity in order to achieve different levels of functionality. So you've got a data link for reliable transmission of data between nodes, a network link for structure management of multi-node networks, and transport layers, so you can actually have reliable communication between points on that network. And then you might want to have multiple communications points between different parts of the network, and therefore you have to have a session layer. And then this data that's being transferred across the network may be compressed, for example, and so you would need a presentation layer to decompress that information before finally it reaches the application layer. And people are familiar in the application layer of things like HTTP for serving up web pages on your computer, job messaging formats, which have been discussed earlier, for example. And this all sits above these layers in a properly defined network transport protocol. But you have to be careful, because if you create a proprietary protocol, it may not contain all these layers, and that may constrain your architecture if you're not wary. Okay, so what additional challenges do we have in actually creating a data pump, other than just pure bandwidth? And okay, so once you've actually got all of this data close to the head, you've actually got to reorder it for printing. Most modern print heads, which actually can eject a high frequency pulse, have rather interesting two-dimensional nozzle plates, and so you're going to have potentially 32 different lines, all needing to be fed at once, and they have to be reordered, and also the sequence within those lines is probably going to be quite jumbled up. You're going to have to meet strict timing requirements. So how are you going to do that? I mean, your PC, for example, if you told your PC to go and do something, it would take an awful long time to respond. It's not a lot of what we call modern operating systems are not what we call hard real-time operating systems. They will struggle to behave in a way which will allow you to actually get a functional product out. You've got RIP processing and interfacing requirements. How are we actually going to connect to this RIP? You've also got to deal with dynamic effects in real time, such as the first drop problem, for example. Or maybe you've got blockages in the nozzle that you want to monitor. How's that all going to happen? So that kind of goes along with standardizing sensor inputs as well, because generally you're also printing to an encoder output. So you have precise timing of where you need to fire the drops with respect to the rig in at least one dimension and potentially more. And how do you actually create a human-machine interface? What does the customer require from you? And how can you provide scalability with excessive complexity to the user? And also, how are you going to generally define your print job? I mean, there are established standards for that, so it makes things a little easier. So the attack strategies that we can kind of wield for these problems are things like divide and conquer. You can have more than one device, whether that be a commercial off-the-shelf server actually doing a RIP for you. You can have targeted processing, so customized IP, which could be doing data processing events on the fly. You can perform actual distributed computing, which kind of covers some of these elements above. And in order to achieve that, you probably need some way of kind of communicating between different parts of a distributed computer, and also scripting the distributed elements and nodes to actually perform tasks. And because we have varying customer requirements, you may wish to actually create extensible APIs to allow a pluggable approach to designing this system. A number of other things which are very helpful are things like auto network discovery. So if you had a system where you could literally just plug in boxes and they kind of knew where they were in the system and how they should interact between themselves, it saves an awful lot of work for people who actually have to do the maintenance of these devices, or indeed the higher level development and deployment. You can also decouple real-time tasks. So we discussed about operating systems and not being terribly good at what we call hard real-time processing, where we need to deal with very low latencies, and so you can have dedicated processors which actually undertake real-time tasks for you. Okay, so how do we actually deploy all this in a modern environment? So, we could consider the ASIC route, for example, but there's huge problems with doing full custom ASICs, not least of it being the immense cost and the risk of having serious problems when things come out of the fab, which you wouldn't have anticipated. And the ASICs are only really relevant for designs which are of the order of tens of millions of products. So when you're dealing with print rigs, where you might be selling 1,000 print rigs, you're just way off the ballpark for ASIC development for that particular aspect. Say, for example, in the ASICs within a printhead, because they tend to have much larger geometries, so physically larger shapes within the ASICs, and they're more developed and older processes, then they can get away with using custom ASICs, and they tend not to be terribly complex either. They tend to rely on an awful lot of the work to be done by the driver electronics themselves. So we're left with things like programmable system on chips, and these are very interesting devices. So these are system on chips where you have high performance processors, such as ARM. I'm sure most people have heard of ARM. If you've got a mobile phone, you've almost definitely got an ARM processor inside that. And a configurable sea of gates, which you can define the functionality of. And so for our markets, this is perfect, because the sea of gates can do the hard real-time problems, and you can create accelerators with them, and you can also add co-processors, and the ARM chips can actually run high-level software. So all these parts here you can actually buy off the shelf. Yeah. So there are numerous vendors like Xilinx, Altera, who will provide you with these components. So they're commodity, they're multi-vendor, and within that programmable logic you can have head data pumps, reordering accelerators, everything you need for a print driver, effectively, give or take a couple of buffers. And they also have what's called hard IP blocks inside them, which do specific tasks. So they're not configurable, but they're very handy. So they have interfaces to standard networks, so Ethernet, for example. And that's a good way of getting data actually into these chips. So you can quite readily run a full operating system on your system on chip. And you can benefit from a huge raft of software and development tools that are available from day one. Okay? So what are the challenges here? Well, the challenges are that you then have to start developing the high-level protocols, the application software, the kernel drivers to interface to your custom logic, the electronics which sits on the outside of the system on chip, and you have to create your own Linux distribution for your target board. And so this is probably a lot of knowledge which you don't really want to delve into if you can help it. So do you have to face this alone? No. We can actually help from embedded IP, so in other words, providing the logic blocks and the kernel drivers to full turnkey drive solutions. Okay? And so we have a retargetable architecture, and it features a number of interesting aspects. For example, we have DMA engines which allow the processor to go about its own business, and for data from memory connected to these system on chips to be sent across to data reordering engines, which then are able to fire data out of the printhead themselves. We've also got some real-time coprocessors which can interpret sensor I/O, such as shaft encoder signals and product detect, and create the right firing pulses for your printhead requirements. And most of that operates without actually even getting the operating system involved, aside from at the very highest levels. And obviously, as I discussed, we have kernel drivers, and we have a controlled daemon which runs on the Linux operating system. So this line here demarks where you go from what we call kernel space to user space, where if you've got a mobile phone or a computer, user space is where you operate all your programs day in, day out. The kernel is something hidden below, which makes everything work nicely. Because we've got a flexible design, we're able to open up a plugin API, and that plugin API is used for distributed job management, peer-to-peer sharing, resource discovery, RIP interfaces, and the sandbox scripting I discussed, so that when you're working in a peer-to-peer environment, you can actually coordinate the operations between the different peers. But you are also able to incorporate customer plugins for your specific requirements. So, for example, in an earlier discussion, we were discussing monitoring the failure of nozzles within a printhead. So the customer could create specific hardware to monitor this. They could develop specific logic, which would go into the gate array itself. They could create custom drivers to actually integrate that with the Linux kernel, and custom application IP, which would actually then be exposed via our Open Plugin API. And our Open Plugin API works in such a way that it advertises services. So once that becomes visible in the software, all of the other services can use it if they're unable to do so. So thank you very much for your time. Hopefully that will give you an overview of the data path.
Thank you, James. Just a question from my side. You mentioned that this board will handle also, let's say, this amount of data, this mass amount of data.
Yes.
Where do you specifically merge master and variable data? Is this on this board?
Sorry, master and variable data. Okay, yes, okay. So when we have data, such as in the coding and marking industry, where you may have a new piece of data which needs to be generated over an image which is pretty much persistent, there's no new information there, that can actually be done on any one of the hosts. Any one of the nodes. So each one of these processing systems effectively has a full operating system on it, and it is a full capability node. So each one can actually undertake that role for you if you wanted to. But in reality, it would depend upon your actual requirements. So you might want everything to be stored off for the unique data in a large silo. It might actually need to be ripped in some way, in which case you could communicate via kind of the RIP API and say, I want this to be ripped, and schedule it so that it then gets transferred across the network to the target in time for printing.
Yeah, I was thinking about keeping that master in there when it's a large page, for instance, where you only need some variable part, let's say 5% variable data, and you could merge that in on this board.
Yes, it's entirely possible.
Can you give us an idea of what kind of printheads you have already supported? Are these already out on the market?
Yes, so we're almost ready to start demonstrating this system with a Kyocera head.
Kyocera heads.
Yes, yeah. The K4A, I believe it's.